Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Rocket Monday, we're going to talk about X-ray, polarimeter, satellite or XPoSat. So let's dive deep into it. So what is this puppy? This puppy is a New Year gift from ISRO to India. This was launched on 1 January 2024 at morning time of 9:10 Indian Standard Time. So it was deployed successfully. We got nominal launch, payload deployment, no problem. Completely going, everything is fine, everything is smooth. Oh, by the way, on top of it, this was the primary mission, but it also had a ride share mission that did require it to decel a bit to step down the orbit, and that India starts to call that ecosystem where they have ride share and they do a lot of complex mission. POEM. So this was POEM number 3. That had 10 sub payloads, so to say. Again, that's not the topic of this video, but those were also successful. So let's talk about XPoSat. Now, it's India's first dedicated polarimetry mission. Now, polarimetry is the critical part. Everything else is like, we got it. Polarimetry, that's damn. So what is this puppy? This puppy is polarimetry instrument in X-ray. Basically, you have to understand almost every wavelength in electromagnetic spectrum, be it gamma, be it gamma rays or X-rays or ultraviolet or optical or infrared, almost all of them have spectrum. Basically polarization. Now that polarization, if you can study that polarization, that's awesome. You get extra depth of knowledge. Now here's the deal. We got that with infrared. We got that with optical. The moment we try to do that with basically X-ray, yeah, it's nigh impossible. So doing that with X-ray, it's damn. So that Polis is that puppy. This one, basically you have anode wire. I do not even understand how the heck this works. Basically, you have to understand X-ray does not refract the same way as a glass tube. So you cannot form image using glass lens or mirrors. So what do? We have grazing mirror like this. Basically, you have like, you just photon glazes around it. So super complex thing. And this was under construction. Be mindful, this photo is from 2013 when they were like working on it. So it was a under construction project for a long time. So polarimetry instrument in X-ray domain. On top of that, it also has a normal X-ray spectroscope, meaning this puppy, this sensor. They have 4 of this sensor. It's gonna do a spectroscopy, which is a kind of known and understood science. Now, what about the range? Now, same way we take infrared, it's huge. So we separated that puppy into chunks. We call it a long infrared, medium infrared, short infrared. So same goes here, but in X-ray, because of the energy level, we found it far more effective to call it based on its energy level. So you have a big puppy that is from 8 to 30 kilo electron volts. If you ever done X-ray or talked with your X-ray technician, they can explain how huge that puppy is. And then you have the smaller one, this puppy, that goes from 0.8 kilo electron volt to 15 kilo electron volt, meaning it's sensitive in that range. Now, there is thankfully a bit of overlap. That is by design and desirable to have a little bit of overlap. Now, project was under construction for a long time, but China's gift that was given to the whole world was painful, and it did cause a lot of delay. Now, be mindful, every nation's space agency generally have a priorities of mission, and some missions would be put on back burner in case of any oops. So that oops happened because of China, so this mission was like kind of shelved. Not shelved as in like we cancelled it. It was just like, okay, let's sort this priority missions in lower capacity. Once we have sorted the flagship missions, then we're gonna make this puppy fly. It was ready to go for long ago. So it was like that happened. So we have 0.8 to 15 kilo electron volt and 8 to 30 kilo electron volt. So there is a very tangible electron band where both of them will help each other out. So this is the instrument. 2 instruments, 2 different ranges with a bit of overlap, and they should be able to study. One should be able to study the spectral analysis of it, and another should be able to study what the heck is the polarization on that photon itself or wave itself. So what's the aim of it? Well, here's to it. To understand this, why this is such a big deal, you have to understand everything, be it radio, be it infrared, be it optical, be it ultraviolet. It always have 4 spectrums, 4 vectors, so to say, 4 vectors of study. Every photons generally have that. So you have photometry, which meaning how intense it is. We got this, we sorted. Then you have imaging. Basically, you do the same thing in 2 axes. That allows you to do imaging. Not only you can tell something how bright it is, you can create a full picture. While creating full picture in optical is very easy because our eyes does that, and first photo cameras did that. Doing that with X-ray turns out very difficult. Be mindful, X-ray does not allow you to use a mirror or a lens. You have to use grazing mirrors. very difficult. So photometry and imaging both were complex topics, but human scientists put forward and they worked it and we got it. Then spectroscopy, so not only we can take the beam of photons, we can split them out and figure out what kind of energy levels they are falling on, and that will allow us to understand much deeper things. That's awesome. Now the last vector, that is photometry, yeah, nobody was even trying to do it. Like, it's genuinely that complex. And to be fair, the sole reason I'm not digging deeper into this mission is like I do not understand polarization. It's like, it's brain damages me every time I try to understand. It's like, you could literally have two axes of polarization, and be mindful, they are called as circular polarization because it's temporal. I to this day do not understand how the heck there is cinema D, I think, the 3D projection, which is clockwise polarization and counterclockwise polarization, and you can wear a glasses which has no electronics and you can tilt your head and you can still see the images. How? But you get the point. Like, it's a polarization is genuinely complex. Not like nobody even tries to attempt it, especially in X-ray. It's genuinely brutal to do so. Now, polarization, now what's the benefit of that? Let's say you go through all these three steps. We have amazing observatory in all those three in X-ray. So what's the benefit of getting this puppy? Well, this puppy has depth. What is that depth? It tells you the emission mechanism, meaning in physics, we know how things happen. But here's the, let's say photon emission of X-ray can happen with multiple ways. You can have like a electron hitting something, you can heat something up, some high energy photon emission from fission or fusion, or like, some sort of scattering. There are many ways how a photons can be emitted. Here's the, if you have this data, basically the polarization data, you can tell this exact principle played a role into it, or what range of it. Of course, it won't be black and white. It's like, okay, Raman scatter only or this only. No, of course, there will be like a breaking radiation and all that. There will be percentage, but you will be able to tell, okay, 80% of this happens because of this phenomenon, 20% happen because of this phenomenon. That's why we really need to go that fourth vector. On top of that, also tells the physical condition. So if you ever studied about this sort of instrument where they are talking about polarization, they will always talk about magnetic field. Because of the integrate marriage between basically polarization and magnetic field, if you have true understanding of polarization of light that is coming through, you can tell a lot about the magnetic field. Like, a lot. Like, whoa. Like, you will be like, this is exactly how the magnetic field is happening. Like, damn. Like, we have studied it with our own instruments, with our own galaxy, and results were like, damn, we did not knew about that. So trust me, there is a very serious need from a scientific point of view to understand this polarimetry data, but we have to build tools to do that. So this exact mission is doing that. So not only is going to tell you the emission characteristics, like what sort of emission is happening, physical condition, what exactly was the magnetic field. So these two are very distinct advantage of either. Before this, we are guessing. Now we have tangible data. Now, to measure the polarization of X-rays from 88 to 30 kilo electron volt, that bandwidth, they're gonna measure the polarization. Now, be mindful, X-rays are very difficult to make wide angle lenses, so it's very small. So what kind of target count we are? We are looking at around 50 potential cosmic sources like black holes, neutron stars, Milky Way center, things of those natures. 50 of those puppies will be the core focus of this band, 80 to 30 kiloelectron volt, where we can detect the polarization. Then we have long-term spectral and temporal study. Now, temporal component is the most annoying part because it changes. That's why we have to keep building new instrument, or heck, sometimes same instrument launched different time gives us different result because of the temporal component. Things change over time. Meaning, let's say we detected a supernova. Okay, awesome. We got satellite. Here's the gas cloud that will be created will expand. It will cool down. What after that? It changed. The spectrum would change. So we need, not only we need to study the spectrum, we also need to study how it changes, and based on that we can infer a lot of other data, distance and all that other jazz. So long-term spectral and temporal study of cosmic X-ray sources, and that should be done in the wavelengths of 0.8 kilo electron volts to 15 kilo electron volts. So that's the whole point of these two instruments. That's their core goal. Now, given the fact that we are getting data from both and there is a bit of overlap, so polarization and spectroscopy, basically now we can counter check it. For example, we detect a X-ray source. Awesome. Now, history. What is the polarization? We can see it. What is the spectrum of it? We can see it. How they are overlapping. Now we can see it. Now we have on paper, we have the mathematics to tell if the spectrum is like this, it should be there. Now we have the instrument to tell exactly how these two are correlating with each other. And again, if our let's say scientific guess is not very precise, we will have the feedback tool to fine tune it. So that's the benefit of having this three mission goals. So one tells you what is the polarization, another tells you what's the spectroscope. On the overlap band, the scientists on the ground, they will allow you to cross-check both of their data, and that would be awesome. And to give you a context how rare this thing is, the flagship X-ray observatory, which is Chandra X-ray Observatory. Yes, it is also named after an Indian Nobel Prize winner. So Chandra X-ray observatory, it has very good X and Y resolution, meaning like in terms of photos, it gives like crisp, awesome images. In terms of polarimetry, it's like nope. It just nopes out of there. It's very difficult. NASA only attempted it right now. Basically, NASA's Imaging X-ray Polarimetry Explorer, yani ki IPEX, is the only one that can reach do this. And as of now, that was launched in 2021. Heck, India was so close to launching it. Like, if that was like so close, so close. Now, this makes India to the only second country that can even attempt it. Be mindful, neither China nor Russia. This is such a deep level of scientific understanding that's like, it breaks my brain. Like, I understand spectroscopy, I understand photometry and imaging. Imaging is, again, that's my job. I understand. But like what? Polarization, how the heck it tells you what is the magnetic field at the source? It just does. So that's the aim of it. That's why it's such a big deal. And having a new year starting with that, that's awesome. Now, I have seen some comments that does show that there is a lack of understanding. And again, I was also that dumb guy. But I would like to share this wisdom. Basically, what is the greater context of all this? Is that astronomy is a research tool that is built layer by layer. And here's the deal, it has no boundaries, nothing. It's just like Chinese people do something, they're gonna share it. Everybody else gonna benefit from it. If European does something, everybody else gonna benefit. Indian does something, everybody else gonna. It's ironically been that since the beginning. Like, very early on, we kind of realized it very early on that this puppy is much larger than any one of us, so we kind of agreed upon it in that way. And sometimes we build different tools, sometimes we build better tools. So exactly, you could have an optical spectrum telescope, awesome. But here's, you're going to build again an optical spectrum telescope looking at the exact same location. Then you're like, what was the point? Here's the now it's better. So you may have gone from 2 megapixel to 12 megapixel. That's the whole point. And all data overlaps. We want overlapping data. It's not something like, oh, what if we spread out everything? No, you want, like, let's say you want to observe a galaxy, Andromeda galaxy. You want to observe that puppy in all spectrum. You want to observe in X-ray, gamma rays, and ultraviolet, infrared, optical, radio waves. You want to overlay all that. You want to have what we classify as hyperspectral data cube. Then you're gonna explore each layer. Each layer is gonna teach you everything. And be mindful, each layer itself has 4 vectors. Not only it has intensity, it also has spectrum. It also has basically the XY coordinate of it that gives you the physical dimension. It's like, oh, this star is here, this star is here, and then you have polarization. So having all of that in that kind of data cube, now you can almost touch it. That's how much data you can get out of it. That's why we built it, and that's why it takes time. So anytime people are like, oh, what was the point of James Webb telescope? It's just a telescope. Again, it's just adding extra layers of data on certain targets, and then we're gonna process that. We're gonna crunch that puppy, and then we're like, some other telescope may be launched in the future. Then it's like, hey, now we can collaborate. Why the heck this was happening? Because of now we have this better instrument that gives us polarization data. And like, I see why it's happening. So that's how it's happened. So if you're like, who found water on the moon? We always knew. That's the ironic part. We kind of knew. Like, you can go find literature very early on. It's like there has to be, like, how we are guessing the formation of moon happened. There is a very good chance it has water. Then Apollo missions, again, there's absolutely good chance that it has water. Then we had flying telescopes, so which are like flying on the jumbo jet, and they're like, oh, we are seeing the deep infrared. We are seeing spectrum of water. Like, awesome, now we know what is there. Then ISRO's mission actually go there and study the spectrum. It's like, okay, now we know what is there. Somebody else in the future will like, okay, this is water. This is the first liter of water from moon. Somebody else will be, this will be the first ton of water. That's how it works. So you have to understand. That's why many times we're going to have similar kind of things where it's like, hey, didn't we just did the whole sky survey? Yeah, that may be done in 2 megapixel. Now we are doing in 12 megapixel. Same thing. So it always goes like VGA 2 megapixel to 12 megapixel to 24 megapixel. Like, exactly, this is Hubble. Now here's the deal. Ironically, you may think this is useless. No, scientists figured it out based on this, that there is nitrogen ice on Pluto. This is another thing. I do not, if they figured out nitrogen with this, I do not want to figure out what they figured out with this. And this was the final photo. So 2 megapixel, 12 megapixel for 24 megapixel. That's how we got it there. And it's very rare, let's be realistic here, it's very rare in scientific community now that you're going to be first with anything, because like there are very few events that are very absolute tip. For example, Trinity test is classified as the millisecond humanity entered the atomic age. Before that, nope. After that, yes. Now, is that same true with the industrial revolution? Hell no. It was a slow gradual process. It was like a plant growing. But there are very rare moments where you can like, though this individual change it, like Einstein, E equal to mc square, before equal to mc square, after equal to mc square. This individual, E equal to say, mc square on paper, E equals mc square in real life. And for many people who like got offended by the fact that he referenced this part, is like, now I have become death, the destroyer of world. What he was referencing, like, which again most people understood it, is that he was considering himself as a warrior who was on a greater quest, like same way Arjun was. It was like quest. The quest was like save your country. In the idea was that he unlocked a door. That door gave natural energy. That energy was equal to mc square. Before this, everybody studied it. After that, it was like, oh, now I understand how big that is. Like, it's one thing, yeah, 50 megaton. It's another to, holy damn, that's 50 megaton. Like, because we never did booms with like, 50 megaton or kilo, megaton or gigaton. We never did that. This was the first time. So that's why he was saying, it's like, I saw, death itself walking away. That's what his, it was not like, oh, I'm the god. It's just like, holy damn, I unlocked the door to like, death, destroyer of the worlds. That's the whole point. And so unless you are Oppenheimer, Einstein, or these sort of things, it's very rare that you're going to be like, oh, we are the first one. You can discover an asteroid and all that jazz, but you won't be like, I am the first individual to propose asteroid. It's like, nah, that we crossed that threshold long ago. So you have to understand. And that's why we're going to have similar things again and again and again and again. You have to fundamentally understand that we are going from 2 megapixel to 12 megapixel to 24 megapixel. Like, and here's the realistic reality. James Webb telescope, thumbnail, look like this. That's it. That's how much area it's seeing. That's it. It does not have enough lifetime to actually scan the whole cosmic universe like this with this resolution. It can't. So that's why you could literally have few years from now an even bigger telescope which looks exactly like overgrown JWST, and we're like, what was the point of JWST there? It's like, no, JWST taught us this. Based on its learning, based on its data, we built a better tool that allows us to, let's say, instead of doing this, scan large area like this. So that's how it works. So that is the greater context in astronomy. We always have to do this. And yes, it does benefit humanity on this planet itself. So it's awesome. So what we can expect in the future? Well, if you have watched my last video, I talked about like a private company, is that ISRO has like two sections. One section is puppy who are building the payloads. Now they are awesome. They're awesome. They're rocking everything. Be mindful, there are only 2 countries at this point in time that has space observatories that can do X-ray polarization. So awesome. No discussion about it. Like, if we say world leading, we genuinely mean it, and it's tangibly that good. So what about the rocket part? Yeah, that part sucks. So the payload part, they're like, bro, we got this. We got this. Just give us money, give us rocket, we got this. And the reason they don't get money is because they don't have rockets. Rocket part sucks. Like in that, I made a like my last video, I made a joke as like, private companies are switching to private players rather than coming to ISRO. Like back in the days, there were only two or three major players: USA, Russia, and European Union. Now there is only 2. So the idea was like there was a new third one, which was basically ISRO. So many private launches happened, and that's how we got the record of 108 launches. So everything was fine, but slowly as SpaceX became better and better, and as Electron Lab became better and better, more and more companies switched. We lost it. Yes, now we are losing our own satellites. GSAT 20 is scheduled to be launched on this puppy. Falcon 9, Block 5. So yeah, that sucks. Now be mindful, this was a very common reality for Indians in the early days. And that was the reason why we built GSLV. We had PSLV very early on, and we had like other variants also, but we realized, we need some big puppy for geostationary satellite. ESA was specialist in that. So we were relying on them, but we built GSLV for that problem. And then why we are using GSAT on SpaceX? Well, it's bit too high weight, as in like not even 1 extra ton. It's like it's a little bit out of the boundary, so we have to use that. And another aspect of it is that money wise, is that same way NASA is getting bitch slapped by Inspector General Office over SLS, same thing is happening here. In India, we call them CAG, Controller Auditor General. Now, they are genuinely mad, and this was a legal court case and all that on Navik delays. Now, here's the deal. India had a war with Pakistan, we call it Kargil War, and Kashmir, in that area, America did a what we call a peace broker, and they trolled both sides. So what they did in American side is like America came to India and it's like, bro, chill. They're like, no, we're gonna boom them. We could have boomed them, and they're like, no, you're gonna sit down. You're gonna say like, no, we're gonna boom them. And it's like, okay, I'm gonna turn off all your GPS signal. Then we had to sit down, and that's why if any of you have watched the movie Border, they're like, that's why we could not had fighter jets flying at the night. We would get lost, and on the other side, Pakistan side, they were sit down. It's like, no, we're gonna boom them. It's like, sit down. No, we're gonna boom them. They're like, okay, we're gonna turn on their GPS. It's like, okay, they sat down. That's how they did peace blocking. Now that taught us a very big bitch slap to India, where it's like, thou shall not have weapons project relying on someone else. So we initiated Navik project. That was our own answer to at least India's local regions in terms of basically GPS requirements, where it's like our ICBMs, our basically aircrafts and all that, we will not need anything else. Yeah, that's behind schedule by so much. It's hilarious. It's like, it's hilarious. That's how bad it is. And Controller Audit General, they were like, dude, we gave you money. This was the timeline. What the F happened? Is the same thing that NASA is going through when everybody asks about like, what the hell is happening with SLS? It's like, you're supposed to be $500 million. This puppy is $1 billion already consumed. Heck, the tower itself is more than $1 billion. And you are saying that you cannot do it somehow under $1 billion with no mathematics. Every mathematics is saying it's going to cost more than $2 billion per launch. So same thing is happening here. So reality is like, if somehow we can have a private company or somebody bitch slapped ISRO so bad that they are like, dude, thou shall stop using 1970s technology. We literally are rebuilding an engine, SCE 200, semi-cryogenic 200. That's literally started its foundation when Soviet Union was around. Soviet Union. So that's the whole point. Like, we have amazing skin, like everything is awesome. Payload department, we got this, we good. It's just that rotten rockets. Our rockets are just not, well, they're literally same way as ESA. The same reason why ESA lost all the contracts to SpaceX. Same thing with us. So I do expect somebody to bitch slap ISRO so hard that they're like, no, thou shall build a new rocket. Thou shall not strap on things to it. Thou shall just build a one competent rocket. But a man can dream. So this was my presentation on basically ISRO's New Year's gift. Hopefully you have liked it, learned from it. In that case, please click the like button, share it amongst a friend. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment because I do try to reply to all of them. Subscribe, press the bell icon if you're free. And as always, thanks for watching.